Hello, everybody. So tonight we're on to the next topic. They go quick in this course. One of the things about this course is sort of a survey of all of School of IT. There are 7 different programs in the School of IT, and well, really an 8th one because there's another one that kind of ties in there. But there's 7 main ones, and we have an 8-module course. So basically, we're looking at a different program every week. Sort of the survey, make sure you're in the right program. Most people come college, start working on a degree, hoping to get a good job, make good money. And all of IT pays really well. I like to point this out. All of IT pays really well, and happiness is worth a lot. So doing the part that you really, really like is worth checking into. So one of the things we look at in this course is just a survey of all the different programs to make sure you're studying the one that most interests you. Get an idea of it, or for most people, it's just sort of confirmation that that's their favorite module out of this course, but maybe you'll see something you hadn't seen before. So last week, we kind of started our detailed study of our detailed survey of the different fields with hardware, the physical devices. And next thing is, what do these machines do? We've kept coming back to this. Well, we've mentioned it a few times, and we're going to keep coming back to it over and over again this semester. That looks really small on the video. Let me write bigger. So data is our raw facts, those no context, so like a number itself. We may have just a number or just a word, and we don't know the sentence that word fits into. Or just the letters, just a single letter, and we don't know the word that letter is going to be used to spell. The raw thing with no context. And what we're really working on here is the flow of the raw facts into information. Again, information is the application. We have to apply some context. I shouldn't use the word application. I'm going to use that next. Data is information is useful data. We know what we can do with it. So instead of the number 17, we throw in a dollar sign, then $17. We don't know what we're going to spend that $17 on, but we know that number is now referencing a budget. We can go to the store and spend that much money. We have some context for it. That useful information flows into knowledge, which is the application of information. We actually use it for something. So with that $17 example, we actually go to the store and buy the stuff we need. Maybe buy lunch for tomorrow. We're doing something with it. And finally, wisdom, which is the insights we gain from that application. In the example I just used, so 17 is a raw number. There's lots of things we could do with the number 17. And at this point, we don't even know if it's a cardinal or an ordinal number, or a nominal number. There's 3 types of numbers. Cardinal is the ones we do math with, so we normally think of. Ordinal is the order, first, second, third. Nominal, we also have numbers that just act as names. So maybe in when we set up group work in a class, right, there's 20 people, and if we randomly assign everybody to groups, at some point somebody is number 17, not their actual name, until we get those groups split up, and then they'll use their name again. So we also have, it could be cardinal, ordinal, or nominal. We have no idea what to do with 17. But to make it useful, we put a dollar sign in front of it, and now we know we're talking about the concept of money. That number is going to be used for trade, some sort of trade. Or like I just said, then the actual application is we spend $17 on lunch. for tomorrow. Which I think I misspelled tomorrow twice there, but I'm just gonna leave it like it is now. Spend $17 on lunch, and then some sort of insight gained from that. $17 is kind of expensive for lunch, right? Compared to like the value menu at Burger King. If we check that out, so like 17 times 7 would be $119 per week at this budget. So the wisdom might be like, okay, $17 is a little expensive for one day's lunch. I go to Burger King and just grab stuff off the value menu, or Taco Bell and grab stuff off the value menu and eat for 3 or 4 days for $17 instead of one day. So maybe the insight's too expensive. Or maybe it was a really, really good lunch. Like, oh, you've been eating the value menu for a while. It's like, oh, I think you spend $17 one day. And it's like, oh, that's way better. I think I can figure out a way to work this into the budget and stop eating the junk off the value menu. I guess they're not really dollar menus anymore. I keep trying to say that. At one point they were dollar menus, but the value menu where things are a little bit cheaper. So we have the raw facts, the raw thing we're working with. Information, we make that useful. Knowledge, we actually apply it, and wisdom, we gain insight from that application. That's the flow that we use our machines. That's what our machines are being used for. That hardware we studied last week, or introduced, it wasn't really in-depth study. The hardware that we talked about last week is used to apply this flow, because this is not new. This is an ancient need of humanity. Computers are just the newest tool for doing this, or probably not the newest tool. The most popular tool for doing this in the modern world. What is it? About 80 something years now. 80 years ago, it was a top secret wartime project that only very few people even knew about. So a little less than 80 years ago, electricity was applied in order to create machines that could optimize this flow. So this part right here, that's the big thing. That's what that hardware is for, to store and transmit data. That's our main goal of the hardware. So that's the next logical section to flow into, I suppose. Let's see. And what I wanted to talk about, well, we discussed that computers use patterns of switches, just a series of switches set to either on or off, really a high or low voltage. But it's good to visualize it. Think about a light switch. Like the light's either on or off. We can use lots of those, create patterns, and symbolically represent raw out of context facts so we know our data. Same way I use the patterns on the board. Drew lines on the board, these patterns. When I draw that, you'll all know what that means already. It's not anything new. It's just we have this agreement. And we assign meanings to them, and there's general agreement on what those things mean. And that's how we store our data. But I wanted to take a little bit and talk about this, because the courseware, that's actually on the major learning objective for the course. People keep adding more and more and more stuff to that. So for those of us on the curriculum committee for that, that's like a big deal trying to get that straightened out now, because it's way too overwhelming, and binary has definitely taken a backseat to that. Last time I taught the course, I downloaded the standardized statewide shell from Ivy Online to use that or start customizing that myself. And binary code the actual representation of how that door data is stored on the hardware. The switches, some switches are on, some switches are off, and that pattern has meaning that we take as our stored data, or similar thing to transmit it across network lines. The storage and transmission that we want from the hardware with our data, it was delegated to a discussion board. A lot of people don't do the discussion boards, which seems to have been happening in our class here. There is a discussion board every week, and I wanted to mention please post to the discussion board. Like talking with a classmate. Well, it's not like talking with a classmate. It's supposed to be sort of the simulation of that. Discussion boards never did that good of a job at it. But in the traditional school setting, everybody shows up at the same time, sits in the classroom, and then heads home at the same time. So when you're walking down the hallway with your classmates, like to, and especially from class, which everybody leaves at the same time, heads back to the parking lot, walking down the hallway, humans are a social species, so people tend to talk to each other. And if the people around to talk to are your classmates, the topic you have in common is that class that you just came out of. That stuff does contribute to your education. It's not a formal part of the education, but it does contribute to it. Discussion boards were an attempt to replicate that in online settings. Didn't work out so well, but it's better than nothing in that aspect. So the standard assignments, they've drifted into other things in a lot of classes. They are just used as writing assignments. I try to make sure they're all discussions. I just had to do this in the database class. I ended up teaching that at the last minute, only had a couple days to get ready. So the first discussion board it just asked for it gave a list of words to define the definitions of. It's like, how do you discuss that with classmates? So I went through and edited them all so that there's something that can actually go back and forth with discussions. And in this class, I did try to set them up so there's things that you can discuss and debate opinions. So like the module 3 discussion board, look at that real quick. I guess the general point I'm kind of rambling on, trying to eventually get to, is please post to those. Last week, only one person had posted on the discussion board. Last time I looked was like yesterday. There was only one person, so there was nobody that could come back and have a discussion with or anything. The module 3 one, I tried to set them up so there is room for discussions. I think this will be an interesting one, or at least I thought it was when I wrote it. So perhaps a little bit of research if you want to research into it, but go back to the most important decades. So back to World War II, or if you want to, you can go back further. Feel free to go back to pre-computer and just the thing that need that computers fill. If you want to go back to there, but back to about World War II, so the 40s, 50s, 60s. What do you think is the most important step from each decade? There's a lot of room for discussion there, right? Because some of y'all might have complete agreement on a certain decade. Right? A lot of stuff happened in the 1960s, but if you sent out a general survey, most people would tell you the transistor was the most important step forward in the 1960s. Because that made computers go from like house size, we say house size, but really it was like a desk size, and then the radiator was the size of a house. But it went from that down to laptops. We couldn't do that without transistors. So a lot of people would say that from the 1960s, but there was a lot of progress in the 1960s. So there's a lot of other things that something you might feel is more important than that. Not necessarily, maybe you're a bigger fan of software, and what people did with the transistors once they were created was, you think, is the bigger step. But room for discussion. Please have your initial post in by Saturday. I'm starting marking points off. If you don't, I'll check. I'm gonna start checking the timestamps because this week only one person posted on that, and there was no way to come back and do replies or anything, which is the other half. So please make sure you get your. Please do those discussion boards. I didn't go with just the writing assignment type of discussions. There should be actual something to discuss and debate on every one of those topics. I tried to find something interesting. And this week should be really interesting. Everybody probably already has opinions about that. Probably don't even have to do research. If you want to do research and do a little bit more, that's encouraged in an academic setting. But I'm feeling most people already have at least half of the decades between the 1940s and the 2020s covered, as far as what you would think the most interesting is. But please do that. But back to the topic for today. In the SDEV 120 class, the binary code was delegated to a discussion. You just talk about binary code. You don't do anything with it. There's not really any coverage of how to interpret it, how to read it, how to work with it, any of that stuff. So I thought it would go nicely in this course. We're following up hardware, so let's see how that hardware, like inside those pieces we were taking apart last week when we took apart the machine and pulled off CPU. Inside that CPU, how are those? That is millions and millions of transistors, millions upon millions of transistors. And transistors are basically just switches. I'll draw it like it is. So, so the way that works is silicon comes in two forms, and we have these two metal plates that electricity can flow through. But there's a chunk of silicon in between them that it can't get across. There's some other stuff. There's some of that has to be oxidized, and so I'm leaving off some parts to try to simplify it. But the electrons start flowing in here, and they can't get across this block of silicon. But we can do other things. I'm going to draw in this picture what's called a BJT transistor. So we have electrons over here and electrons over here, and this one works with current. The one that's actually on a CPU would work with voltages instead of current. Voltages are potential for electricity to flow, and current is when it's actually moving. And when it's actually moving, it's going way too quick for us to do anything. So we set up all that potential for things to happen and then let it run. But there's a lot more steps. So one way to think about it is with these multiple types of silicon, the electrons coming in here, there are two types of silicon, N type and P type. And the N type, we can think of that as having extra electrons. We take pure silicon, which is very balanced chemically, and chemistry class is very, very balanced, and we dirty it up. We add things that either have an extra electron or one short of an extra electron. Phosphorus and potassium are the most common because they're cheap and readily available on Earth. But there's lots and lots of other things we can do. But we throw them in there and basically dirty up that pure silicon, so it's not perfectly chemically balanced anymore. Some of it will have extra electrons. N-type silicon has extra electrons, and P-type silicon is missing electrons from that perfect balance. So one way to visualize this, an analogy, a good way to visualize it, this is how when we think about it and start doing stuff, is those extra electrons. You can think of those as plugs. This is a standard terminology we'll hear in like electrical engineering classes. And the P-type silicon that's missing electrons, think of that as holes. So the electricity can't flow because those electrons start to move across there, they fall in one of the holes and get stuck. So it can't go all the way across. But if we added a third line in here, where we could send in electrons and fill in all those holes, then our plugs could flow across there. That's the standard analogy of how it's working. I guess since we're in a classroom setting, I'll set up the whole thing properly. So we have a three little pieces, the N-type silicon. So the N-type silicon has extra electrons. That's where the analogy comes from, the plugs, but electrons are subatomic. So the plug and hole analogy falls apart because electrons are before the level that would have any substance, so there's not really something there. That's getting a little complicated, but they have a negative charge. So that N silicon has a slightly negative charge, and the P silicon has a positive charge. And just like magnets, opposite charges attract. So right here near the edge, electrons are going to come over to this edge. Some of these this positive polarity will flow right across that edge, attracted to that, and vice versa. So we end up with this nice positives and negatives right at the edge. So it's extra and missing electrons, and right at the edge where they meet, some of them can flow across on their own, and we get something fairly stable, which you've probably heard electricity is always trying to find the route back to ground. The reason it's doing that is because that's a stable state. Electricity is just looking for a stable state. So when we get even a small bit of stabilization there, with all the positive polarity attracted over to the N-type silicon and extra electrons attracted to that P-type silicon, it stabilizes at the edge, so electricity is no longer going to flow. So then we throw in another current to add a whole bunch of negative here in the middle, and that messes up that stability. And at that point, the electricity can flow through. That's how a transistor works. So we turn it on and off by applying voltage. So on an NPN, we add a voltage to turn it on, and then turn that voltage off to turn the transistor off. We can do it all the other way as well. We can have PNP, where we apply a voltage to turn it off and remove the voltage to turn it on. It works both ways, but it's that little difference right there. So it's really just a switch. That instead of that physical device like a light switch that you're used to, we use more electricity to turn that switch on. And these can be very, very small. People have recently announced they've figured out ways to pass the theoretical limit of how small we can make those.
So for more power, would you have to make a bigger one with more holes? Because what if the current you're trying to switch on and off fills up the holes?
And, so that's just an analogy. It's really the polarity there. And as far as bigger, it can overload basically. But yeah, so that is the analogy still kind of holds that way. The analogy falls apart on PNP ones, because then we have holes trying to make it across plugs. I guess it's like a ring toss game, maybe. And there's so many that it's going to get caught on the way across. But it's an analogy to think about it, because we're humans. We think better about a little physical ball that we call an electron actually moving. But it's like a magnet, or the electron is really like the stuff in between the magnet. Not the magnets themselves, but what's happening in between the two magnets. The electron's part of that. And when we get enough of them together, then we start to get substance. So, yeah, electrons are below the part of the universe that would have any sort of matter. But yes, we can make them bigger and bigger and bigger. There's a thin protective layer. So like the ones on the CPU, there's 3 chunks of metal. And then we'll have our 2 types of silicon. And then there's an oxidized layer of silicon separating the metal from the thing. Oxidation is like rust or tarnish on copper. I get that. When in the presence of oxidizing, it changes. Usually it gets harder and stiffer, and the properties change a little. So really, for your question, Hunter, the power has to do a lot with that oxidation layer. Actually, you'd almost think of it as like turning it to glass. Not quite that far, but silicon is one of the main ingredients in glass. So we made it harder. So it starts to get some insulator properties. So the thicker that insulation, the more voltages we can pass through our wires without frying up the critical part. But we have a bunch of switches. So how do we represent our data with that? How do we get to our numbers? This is when a lot of people are just curious about coming in. So that's our main topic tonight, binary representation. Of data. Also hexadecimal when we get to the end, because binary is hard. So actually the binary is too simple for the human mind. I say hard, but it's hard for us. And the thing that's hard for us about it is it's too simple for the human mind. So we actually make it more complicated so we can work with it without confusing ourselves. So let's take a minute to look at this. And what surprises a lot of people, if you've never seen it before, is it's actually something you already know. You just might not know that you know it. And the class where it's traditionally been covered has been filled with so much information that it's overwhelming that even when it still fit in there, it was just lost in the mess somewhere. So we're working on cleaning that class up. At least as long as I'm the vice chair of the software development committee, or sitting on the software development committee, it's going to be reminded. It's going to come up first thing every single meeting. But it decided to cover binary somewhere else. Thought that would be useful. So to start with, you might have to think back to elementary school. If I write this on the board, you all know what that means, right? But do you remember way back in elementary school where you learned how you know what those symbols mean? It has to do with our columns. So in this column, we add up a bunch of ones. In this column, some tens, and in this column, hundreds, and we can continue that on to a lot of columns. Right? The pattern just continues. Well, these are all patterns of 10. So 100 is really 10 squared. 10 is 10 to the first power. And there's a rule from math that any number raised to the 0th power, any number, if we raise it to the 0th power, equals 1. I always like to think of it as we have something, otherwise we would have wrote a 0 here. But if we think about exponents as repeated multiplication, we don't have any of that something. It's not 0, but it's not really that thing we're looking at. So we just go back to our default number. That's one way to think about it. There's different ways, but it's just a rule in math. It does kind of fall apart at indeterminates with 0 to the 0th power, because we have that rule that anything raised 0 raised to any power is going to be 0. So which one of those rules takes precedence? But that's something different altogether. Our rule says any numbers, so to match these other columns, we say that first column is actually 10 to the 0 power. Everybody remember doing that way back in elementary school? And then we know what this means because we have 2 10 squareds. So we have 2 10 squareds, plus we have 7 10 to the first power. 7 times 10 to the first. Plus we have 6 10 to the 0 power. I already wrote them, I started with what they were at, because I think most people are used to these numbers. We don't think in powers of 10, but we write them down. So 2 times 100 gives us 200. Plus 7 times 10 gives us 70. Whoops. And 6 times 10 gives us 6 times 1 gives us 6. And that's where we get the meaning of that. Does that ring a bell from way back in elementary school?
We didn't touch this till like late middle school.
Oh, somewhere along the line. You've seen it before though, right?
Yeah, he discussed this yesterday about mine.
Yeah, so there's so we have that general thing there, and then we work in columns, right? If we wanted to say take 23 minus 17, or I'll do plus 17 first. We work down our column. 3 plus 7 gives us 10, but 10 requires 2 columns. So we take a 0, so we have 0 ones and 1 left over into the next column. So it carries over. And 1 plus 2 plus 1 brings back to 4. Or subtraction, we can do a similar thing. 23 minus 17. We work one column at a time, and well, if we want to stay with positive numbers, 7 is too big to subtract from 3. So we can borrow some from that next column. So we're left with 1 in the next column, and then we have 10 plus what was in there. So 13 minus 7 is the number we can find, and we work entirely in columns. The thing is, there's nothing special about base 10. 10 is just convenient because humans have 10 fingers. There have been lots of bases over the years that have been used. Mayans always use base 20 because I guess they wore sandals, so they had their toes readily available too. So 20 was a more convenient number for them. Base 60, that tends to throw off Americans. Let me turn my video on real quick. It sounds like so much if we're used to 10, but actually base 60 is counting on your fingers as well. I'll put this by the video because we have different sections of our fingers. So if you count those sections, like use your thumb to tap up against one, then there's 12 different sections on the finger. So, and then use fingers on the other hand, and then you can count to like 12 5 times with just your fingers, or like on a clock, you can count to 5 12 times. So base 60 is still just using our fingers. It throws people off because there's a big number. But that's the only thing special about 10 is we're humans and we have 10 fingers, so that's a convenient number for us to work with. We can use any number. Let's pick a random one along the way. So just one in the middle on the way to where we're going, maybe lucky number 7. Base 7. So the thing that we raise to a power to give each one of our columns, that's the base. That's what we're basing all of our numbers off of. So 7 would be similar. We don't need all our digits though. In 10, we need, for base 10, like we know, we need 10 digits. 0 through 9, the ones we're used to working with, but we need one symbol to represent everything in the column. So if we're in base 7, we only need 7 digits. So symbols 0 through 6 will be enough to represent any number. I'll do 4 columns and just make up some number here. So 0, 3, 4, 1. And just like in base 10, the power pattern will continue indefinitely. We're in base 7, so everything here is a power of 7. 7 cubed, 7 to the 0, 7 to the first, 7 squared, 7 cubed, 7 to the 4th, to the 5th, to the 6th. We can just keep going, the columns going forever on that. So what number, as far as value, are we representing with this symbol? Or this set of symbols? And we would calculate it the same way we did this. So we have 7 cubed is 343. If you don't have that number memorized. Some of y'all probably have 49 memorized for squared. Obviously 7 to the first power is 7. And then that rule, anything raised to the 0 power is going to give us 1. So we have 0 343s plus 349s, 4 7s, 4 times 7, plus 1 times 1. So if we add that up, what is that? 3 less than 150, 147. Plus 28 plus 1 is 1 less than 177. 176 in base 10. So the numbers we're familiar with, as these symbols have the same value as the number 176 as we're used to it. Pronouncing it's a different thing because we're English and we don't really have words for the base 7 ones. But you see, there's nothing special about that pattern. We could add and subtract numbers. So 176. So what's 176 minus like 83? Let's do some subtraction here real quick. We know what 176 is in base 7. That's 0341. Find 83. We have to figure out what the columns would be. So 7 to the 0, 7 to the first, 7 squared, that's probably enough. So I'm going to start with the biggest column. 7 squared is 49. How many times will 49 go into 83? Which I tried to phrase that the way that should sound familiar back to elementary school and writing out division longhand. 49 will go into 83 one time, right? 1 minus 49, and that leaves us what? 34. So 1 with a remainder of 34. So we have 1 in that first column. Now, how many times will 7 go into 34? Seven times 5 is 35, right? So 5 would be too many. That's the way I do division. I just start going with numbers until I hit one that's too big. And it's got to be one less than whatever's too big. Minus 28. I believe is 6. So 4 with a remainder of 6. So in our 7th column, we have that symbol 4, and then there's 6 ones left over. 146. So now we can do the same thing we did before. So 1 minus 6 would be too big, so we need to borrow from the next column over, right? I'll leave a 3 here. And plus. Our base is always written as 1, 0. In base 10, 1 in the 10s column, 0 in the 1s column. In base 7, if we wanted to write a 7, we'd have 1 in the 7s column and 0 in the 1s column. So the base is always written as 1, 0. So 10 plus 1, which I was just writing it that way to express that point. Really, we're borrowing 7 from the next column, right? I'm going to write it this way so it makes more sense to us. So we borrowed 7. So that's what our next column's worth. And 7 minus 6, we know what that'll give us. 3 minus 4, we can't do that. So we'll borrow again. Then we get 7 plus 3 would be 10. Minus 4 gives us 6. And 2 minus 1 gives us 1. So in base 7, that's what we get when we subtract. Unless I made a mistake in the, when I was doing the math and talking at the same time. But now we can figure out what this number is. We have those 3 columns. 1, 7, 7 squared or 49. So we have 149, 1 times 49. And we have 6 7s. And then we have 1 in the 1 times the 1 column left. So 49 plus 42 is 80 plus 11, 90 something, 91 plus 1. I think I made a mistake somewhere. 49 plus 42 is not 91. Yeah, that would be 91. Plus 1 is 92. What should this be? Should be 93. Uh-oh. I done drifted away from my notes, didn't I? Oh, whoops. I did 7 minus 6. Just like when we borrowed from before, we added to what's in that column. So 7 plus 1, we'd call that 8. And 8 minus 6 gives us a 2, right? So then 91 plus 2 gives us 93. Sorry, it works out much. It's a much better example when I don't make the silly math mistakes along the way. 7 plus 1 is 8, not 7. But we get the same thing. We can see nothing special about 7. So we can use whatever the most useful base is. We can choose whatever number works best in the situation we're working with. In machines, we're a bit more restricted. Because for machines, that can go all the way back. Oh, we can go all the way back to just 2 numbers and use values like true and false, yes and no. Yes and no are much more useful ways to put them. And that relates very nicely to the machines, because then it could also be used as on or off. It's okay if I erase all this. Sorry about the addition mistake, but no matter what base we use, we'll get the same. We get the same result. There's nothing the mathematical concepts do not depend on the symbols we're using. So we can use any of them.
Like calculus again.
Yes, there are some great tricks in calculus if we change the base. Usually we change it to E, but
One of those difficult things was trying to learn a calculator. Way too many buttons.
oh yes, like a TI-84.
84 or TI it is. It's just one of them.
One of the nicer yeah, any of the nicer TIs. There's so many buttons on those. Every once in a while, it's nice to go back to just a basic calculator that just does those few things we need.
Firmware update on them, so it's like, oh.
Yeah, so using that, taking that concept further, we can get all the way down to our 2 states and work with and use mathematical representation on a binary state machine. So then we can start doing stuff with it. In our case, we're mostly going to talk about storing data. So we just want the patterns, but that adding and subtracting through columns will still work. And usually we just choose one, since I don't think we're going to have time to get there this evening. When we're talking about it, as humans, we usually talk about addition, because that's what we do. That's what we build all of our math off of. But we can also build it all from subtraction. And the machines themselves build it all from subtraction. And if you think about it, you don't have to think about it very long to figure out why. If we start adding voltages and something goes wrong, we could end up with a whole bunch of electricity really quick, right? Like fire risk levels of electricity, or at least shock levels of electricity. But if we base everything off subtraction instead, and we're taking values away, if something goes wrong, the electricity shorts all shorts to ground. So we go back to zero. So it's much, much safer to build it all off subtraction, but because most humans think about addition, when we're talking about it, there's that discrepancy. So there are some discrepancies in there, but wait a minute, it's basically gonna be the same thing. Which way did I do it first in the notes? Works with any numbers, so I'm just gonna write 8 columns here. 1, 2, 3, 4, 5, 6, 7, 8. The big thing is how many symbols do we need to represent any given number? Obviously, the bigger our base, the fewer symbols we need to represent it. So in base 2, also called binary. I'll make a list of the ones that have names. Base 10 is decimal. This becomes important because we still have fractional values. So we put a little dot in between them. But decimal is not the name of that dot that separates the whole number part from the fractional part. It's called the mantissa. Nobody knows that word. But we don't want to use decimal point because decimal refers to base 10. So if anything, we'd want to maybe say binary point. The actual term is mantissa. But nobody ever uses that outside of a formal lecture where they say, okay, the actual name of that is mantissa. And nobody remembers that. But we have our same thing. We're all working in powers of 2. So for binary or base 2, we need 2 symbols. And we need them to work with math, so we want to use our digits. So it makes sense to start with 0 and 1, but there's an extra reason for 0 and 1. Another thing about our first 2 numbers, they're also very, very easy to write and tell apart at a glance. Right? We could use true and false. True and false tend to blend together, right? Can I draw one of the fancy words? You may have seen people write really sloppy, almost like it's cursive. And where the T and the F blend together, I can't do it very well. A really sloppy A, so it looks like an R. And write the word true and false blended together. So anybody ever seen pictures of those? Some people are really, really good at it. Like you can look and it's almost impossible to tell which one they were trying to work. People trying to cheat on a multiple choice quiz doesn't work when you click a button with a mouse, but some pictures of those things still exist. But 0 and 1, the numbers we would most like to use also happen to be quick and easy to write and easy to tell apart at a glance. And that's another big thing for them, is to tell them apart at a glance. And also notice that I do just do a vertical line when I write binary. I usually write the serifs because vertical lines might show up in lots of places. Actually, let me do a quick little sidestep. I do all those little serifs on the 1 because on a very important math test, I'm actually a math person. So I was nearing the end of my bachelor's degree, and on a very important test, 301 times the natural log of something showed up. I wrote it like that. I wrote my 1 and the L the same way. So y'all can probably guess pretty quickly what happened on the next line, right? One of them disappeared on the next line, and that was a very important math test. So after that, I always started writing my 1s like that and my L's like that to avoid the silly little mistake that should have been easily spotted when I wrote it the first time. It's like those are 2 different symbols written right next to each other. But that's why I write my 1s like that, but I'm not going to do that in binary. So I just do regular ones here. But we have the same numbers or the same pattern to represent are numbers. We have the same value, different symbology for it. Lots of ways we can say it. And there's another really nice advantage to this. 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th. We need a lot more columns to write any given number. Y'all probably know a lot of these. Anything raised to the 0 power is always going to be 1. And then we double it. 1, 2, 4, 8, 16, 32, 64, 128. So an 8-bit number, and the pattern just continues, but it takes a lot to write them on the board. This is not something new. This is how Egyptians did the math. And Egyptians used base 10. It's just like us, they had 10 fingers. So they had all the symbols. But when the scribes went to do math, they would use binary. They would switch it to binary, do the math, and then switch it back to base 10 to write it down. I had to learn that in the history of math class. And it is actually a much quicker way to do it if you don't have a fancy machine to do the math for you, because there's a lot less room for mistake. So let me make up one here. 1 0 1 1 0 1 0 1. So what number is that? And here's the thing that makes the binary so much easier. The nice thing about binary makes it easier, like why the Egyptians did their math this way. So on those last ones, we always had to say, like we had a 6 in that middle column, we had to say there's 6 of those. So 6 times something. But in this one, well, there's a 1 in the 128 column. We get 1 times 128 plus a 0 in the 64 column. And there's other terms that we could use to represent binary, in particular yes or no. So we're only ever going to multiply something by 1 or by 0. What happens if we multiply something by 0?
0.
Goes away, right? So really what we have are yes or no questions here. That multiplication step, we can ignore that and just, yes, we have 128. Plus, no, we don't have any 64s. Yes, we have a 32. Yes, we have a 16. No, we don't have any 8s. Yes, we have a 4. No 2s. And yes, we have a 1. So it becomes a yes or no question. Makes it a lot easier to do math without a fancy machine. That's why Egyptians would do it that way. They wrote base 10. They had 10 symbols like we did. Theirs looked better. They had flowers and birds. Even in the quick writing, when they did numbers, they still used flowers. And it wasn't like the hieroglyphic birds, but it was like a quickly drawn bird and an insect. So they wrote in base 10 and talked about base 10, but they switched to binary to do their math. So it's not a new concept. And then what do these add up to? 160, 176, 180, 181. So that's the same value as 181 as we would know in base 10. That's the basic idea of the representation. It can go both ways. Does anybody have any questions about that? Has everybody seen it before? In our society, it seems to show up places. We just want to make sure it's covered someplace clearly. So if we had another number, another integer, so let's say 217 in base 10, and we want to know how to write that in binary. I'm set up 8 columns again. 4, 5, 6, 7, 8. 2, 0, 2, 4, 8, 16, 32, 64, 128. So if we need to convert this number into binary, we can go back to that yes, no thing or just subtract. Do we have any 128s in 217? I see heads nodding yes here. So 217, whoops, minus 128 is going to be more than 0. So yes, we have something in that column. What do we have in that column? It's almost like minus 100, except 11 off 89. Is that right? Or did I go the wrong way with 11? Yeah. Yeah, 89. I do approximations and stuff when I calculate it. Did you just punch that in the calculator? Okay. I might have gone 11 the way. It's 11 away from 100 off. But when I wrote that down, I suddenly started questioning whether I should have went 11 the other direction. So we have 89 left. Do we have any 64s? So heads not in here. Minus 64 leaves us 15 or 25. So do we have any 32s? Nope, that would be too big. That put us below 0. We'll have a 16. That'll fit. So minus 16 leaves us 9. 8 will fit there. Minus 8, and we just have 1 left. So zeros till we get over to the end. Addition and subtraction in columns work the same way. So let's do like 13 plus 5. That way we don't have to get very big numbers here. So 13, we can do both of these in 4 columns. 1, 2, 4, 8. Yes, we have an 8. Leaves us 5 with 5 remaining. 4, so yes, we'd have a 4. 5 minus 4 which leaves us 1. And a 5 is 0, 1, 0, 1. I drew that on day 1 of the class and just mentioned that. It's just like the symbols I'm drawing up here. They have meaning because we agreed they have meaning. This is the difference in where AI sets in. I'm not a big fan of the intelligent part because it's not really intelligent, but what's so different is traditionally we forced our pattern onto the machines, and with what we call AI, we let the machine pick the best pattern. So it's still just matching patterns, it's still just following patterns the same way, just we let the machine pick the pattern that was best for it instead of using the human pattern. But when we add, we go through the columns, 1 plus 1. How much 1 plus 1? But 2 is written as, that's our base. So the base is always written 1, 0. So we can't fit 2 symbols in 1 column. So we write that, carry it over to the next column. 1 plus 0 plus 0. 1. 1 plus 1 against 2. Carry your 1. 1 plus 1 is 2. So 0. We carry a 1 to the next column, which we don't have written, so we have to write that down. And we get that number. So it took more bits, but 1, 2, 4, 8, 16. Don't have any 8s, don't have any 4s, and we have a 2. 16 plus 2 give us 18, which is what we get when we subtract those, right? Or a similar thing with subtraction. Do I want to use those numbers for subtraction? I do not want to use those numbers for subtraction. So let's do 13 minus 10. Yeah. So 13, we have that row right there. 1, 1, 0, 1. Minus 10, we would have an 8. 10 minus 8 is bigger than 0. So yes, we have an 8. Leaves us 2, so we don't have any 4s. Have a 2, and then that gives us a nice round number. So we're subtracting. 1 minus 0 is how much? That one's easy. 0 minus 1 is like what we had to do somewhere that's already been erased from the board. 1's too big unless we want to go into negative numbers. So we need to borrow from the next column. We had 1 here. So if we borrow one of those, we bring a 1, 0 over here, which is really a 2. So 2 minus 1 is how much? 1, right? We borrowed from this one, so we don't have anything left here. 0 minus 0, 0. 1 minus 1 is 0. So we have something in the 1's column, something in the 2's column, and nothing else. So 1 plus 2 should give us 3. So you can see the addition and subtraction work the same way. It's not actually what the piece does, because there's a slight problem if we try to go to negative numbers. I think I can cover the little problem really quick. It's actually called the 0 problem. Because what's our first thing? What do we do for positive and negative numbers in base 10? Just add another symbol, right? It's okay if I erase this part over here? Zero problem. So in base 10, we just add another symbol to say something's positive or negative, right? Positive 23 or negative 23. And we could go on and on with numbers like this, right? I could add a big list, positive 7, negative 7. And we always have 2 pairs. Our number line is symmetric. Got 0 in the middle. We got a positive 7 and a negative 7. A positive 23 or a negative 23. What about this? That seems a little nonsensical, doesn't it? Is 0 positive or negative? It's neither one. So 2 values for that starts to cause a problem. If we're in binary, it's okay if I erase this half of the board. Binary fills up a board really, really quick. So this is a little step to show what the machines actually do. I just wrote 2 problems to show that. Addition and subtraction, they're very different, right? One of them carried things to the next column, and the other one borrowed stuff from the next column. So in order to do that, we would have to build 2 different circuits. One that borrowed from the next column, and another one that carried things to the next column. So it would be really nice if we could define it all with one symbol. Kind of like we do in math class, where maybe 7 minus 3, we think of that as 7 plus negative 3, which is still kind of the way it works. But when we build the circuit, we always use negatives. So if we want addition, if we wanted 7 plus 3, we could do 7 minus negative 3. So technically the circuits would build off that to get 7, the plus from minus the negative. But we can build all of our math from one operation that way when we define it as negative. So if we start trying to define negative numbers, we kind of hit a problem at 0. We can use a 1 or a 0, that extra symbol. We only have 2 in binary because we want to do this in a machine, which means we can't just make up another symbol. Our switch is still either on or off. We don't have a different type of switch we could add in there. So we could just define things, and we could say we'll add an extra bit. Extra bit. 1 is, let's do negative. And 0 is positive, And we can define that any way we want. It's unique to the machine. It is not consistent standard across the board. So if you're looking at something and you know you have a bit on there representing negative and positive, you need to know for certain which one is which in the particular machine you're working on. So then if we had like positive 23, we need 5 bits to do that. No, we need 4. Oh, 5. 1111 would be 15. So we need to double that in order to get to 23. So we have a 32, a 16, 8, 4, 2, 1. So 23, yes, we have a 16. 16 plus 8 would be 24, so that's too big. Nope, none of those, but we do have a 4 to get us 20. We went 23, so there's 23. So a positive 23 would be plus 23 would be 1, 1, 0, 1, 1, 1. And negative 23, oh, I wrote that backwards. I just defined it, positive 0. So kind of like we're defaulting to positive, and if we flip the switch, then that becomes negative. Negative 23 would be 1, 1, 0, 1, 1, 1. So that works. But it's even more exaggerated than this because we're talking about a machine. So we have to have that bit there, which means we have both 0, I'll do it with 4 bits, 0, 0, 0, 0. This one means it's positive 0, or we have 1, 0, 0, 0, 0. So we have 2 unique representations that give us a positive 0 or negative 0, but we don't have 2 zeros. We have 2 of every other number, so that's what throws our math off. It throws our math off. We need a way to fix that, and we use something called 2's complement. Can I erase this section over here? So there's a thing called 2's complement. Complement with all E's, not any I's in the word. We're not saying nice things about our number. And the 2 is not binary. That 2 stands for second degree complement. It's this is an old long known thing about math that this pattern works out. But the thing is, with like base 10, it's an awful mess. With any base other than 10, it's a mess because complement gets fairly complicated. Like what would be the complement in base? Well, the complement is always what it takes to get to our highest digit. So in base 10, our highest digit's a 9. So if we had a 7, the complement would be 2. If we have a 9, the complement would be 0 because we're already at our highest digit. If we have a 1, the complement's 8 because that's what gets us to the highest digit. And then we do all this complementing things to get the first degree complement, and then we take the second degree complement, and then if we add 2's complement, the second degree complement number, we end up with what we would have got if we subtracted plus an extra digit. So it's great for machines, but it's a mess in all those bases because we have to stop and think about what the complement is and figure out where we're at. However, I just gave the actual definition of complement, not the one we normally hear in an IT class. Then we get to binary. We have 2 symbols, 0 and 1. So following that definition, what we need to get to our highest digit is even easier because we only have the one option. If we're already at 1, then we'd add a 0 to get to 1. If we're at 0, we'd add 1 to get there. So the way it's normally stated when we're talking about computers is it's just our other digit. The complement's the other one. And then it's kind of, we can think of it like complementary colors. Like the ones across from the wheel, there's always the 2 that go together nicely. When we get to binary, two's complement becomes really, really easy. So we take complement, take the one's complement. Again, one is the first degree, we complement it once. And this two's complement, if we just complemented the whole thing again, we'd get right back to where we started. In any base, not just in binary. If we took a complement, we'd have all the complementary numbers. So if we took a complement again, we'd get right back to where we started. So for the second degree complement, we add one. So we take the complement, then we add one to that to get the two's complement. And then we keep adding one to get the next degree complement. So add one to the two's complement and get the three's complement. Or third degree complement, four's complement. And we don't necessarily need to worry about all of that part. Oh, I forgot to ask about erasing. Hopefully it was okay if I erase that. So this is what machines actually use, because then we can do it all with one operation. And we only need to build one circuit to do all of our math. Then addition and subtraction are the same, and multiplication is just repeated addition. Subtraction is repeated division. I said that completely backwards, didn't I? Division is repeated subtraction. You know, known as in elementary school. So we just build it all from one operation. Addition, I'll talk about it in terms of addition because that makes more sense to people. We add, straightforward, add the negative and get subtraction, add repeatedly to get multiplication, and repeatedly add the negative to get division. And we build all of our math that way. So two's complement, let me just make a couple numbers. Well, I'll use the same ones we just did. 13 minus 10, the one we had to borrow from. So let's switch this into an addition somehow. So that's what I erased off the board. 13 is 1101 and 10 is 1010. So we have that spot where we had to borrow before. But we want to do it all with one circuit, and carrying is easier than borrowing. So that's the circuit that we usually build. And then it kind of switches around to avoid like voltage spikes. Then I'm going to use those symbols I just defined. So 0 is positive, 1 is negative. So instead of 13 minus 10, I want to think of that as a positive 13 plus a negative 10. Then we can take the ones complement. And the 13 is not changing because that's positive. This is how we get our negative numbers. So 13 stays like it is. Positive 1101. And the negative 10, we want the two's complement. So first off, we have to take the ones complement, which in binary is really easy. That's just the other number. It gets to be a mess in any of our other bases. I used to try to periodically show that it worked in base 10, but it's a confusing mess keeping track of all the complements. It's really, really easy in binary because it's just the others. So every place that's a 1 becomes a 0, 0, 0, and the zeros become ones. 0, 1, 0, 1. And now to that, we add 1 to get our two's complement. So the 13 stays like it was. 0, 0, 1, 0, we need to add 1. 1 plus 1, that's easy, right? The biggest we'll ever get this way is 1 plus 1 plus 1 if we have to carry something. So we never get bigger than 3. 1 plus 1 is 0, carry 1 to the next column, 1, and then there's nothing else to carry, so everything else is just going to copy down. So negative 10 as 2's complement would be 0, 0, 1, 1, 0. And now we can add the 2's complement, and that's the same as adding the negative. This is how we write negative 10 using that notation. 1 plus 0 is 1. 0 plus 1 is 1. We've seen all the combinations already. 1 plus 1 is 2. So in binary is 1, 0. The base is always written 1, 0. So 0 carry a 1. Then we have 1 plus 1 plus 0. It's 2, 0 carry a 1. I guess we haven't seen 3 in this step, but 3 is 1, 1. So it follows the pattern. 1 plus 1 plus 1 gives us 3. 1 plus 0 gives us 1. So now this number tells us the answer. And this, I mentioned just very briefly a second ago, from 2's complement, no matter what base we use 2's complement addition on, we always have an extra digit. Sometimes that extra digit is going to be 0. But we look at that bit, and it's going to get discarded. It's in our sign spot, right? It's either positive or negative. So we're going to discard it, but we look at it first. Is anybody heading on to a 4-year degree after this? Maybe. When you take a class on assembly language, which if it's just an elective, I would highly recommend. Machines can only do simple things, so assembly language is actually a lot easier than our high-level programming languages. But at some point, you might want to take that class. I would highly recommend it. This is a very, very important bit in assembly languages, jump on carry. That'll be important for some of y'all later. That's the bit that is used for jump on carry to get to assembly language. Whereas now we're just throwing it away. The voltage flows back to ground because we only have 4 spots for a number, not 5. Since this is our negative sign, it kind of switched. So if we get a 1 there, that means we have our answer. So 0, 0, 1, 1 is a 3. Let me quickly do it the other way. So if we did 10 minus 13, 1, 1, 0, 0, 1, 0, 1, 0, and 13, negative 13 would be 1, 1, 1, 1, 1, 0, 1. If we did it this way, we'd end up with a 0 there. If we have a 0, that means we got the 2's complement number, so we have to bring it back to the positive answer. But this gives us a negative number, right? So that should make sense. 13 minus 10 is positive. Our symbol for negative and positive switches along the way, which also happens if we did base 10 2's complement. So when we see this 1 here, before we discard it, we know that's our correct answer. If we did this the other way, I'll just switch these real quick. 0, 1, 0, 1, 0. Switch all these zeros to ones. Or all the ones to zeros. So 0, 0, 0, 1, 0. And then adding 1 is really easy on that one. 0 plus 1 is 1. So just change that last symbol. 1, and we get this. We have a 0 in this spot, so that means we actually have the negative number. So to find the actual answer of 10 minus 13, well, this would be the actual answer because this is negative something. But to find out what that value is, we subtract 1, which gives us 0, 1, 1, 0, 0, and then turn that back, and then the complement. So complement that 1, 0, 0, 1, 1, which back to these symbols, after we complement everything, notice we got the sign for -3. So that's what the machine's actually doing. I was hoping to finish that a little bit quicker, but does that make sense? See how I have that nice pattern? Take the complement, add 1 to get to the second degree complement, and then we only need 1 operation, which translating that back to hardware means we only need 1 circuit to do the calculation. I'm gonna finish that about 5 minutes ago because it's about break time. After the break's gonna be a little bit quicker. But does anybody have any questions about that first initial representation? The big one's the integers, and then this is what machines actually do when they do the process. To do the subtraction, and then we can do all the comparisons, because if we subtract 2 numbers, we know whether they're bigger, smaller, or the same. Subtract 2 numbers, if you get 0, they're equal. Subtract, if you get a positive number, that means the first one was bigger. If you get a negative number, that means the second one was bigger. So that's how we do our comparisons, and that leads into all of our processing. But a little bit more to talk about it after a break. 10 minutes sound good to everybody? All right, that went about 5 minutes longer than I planned. So we will get back to it at 7:31 on my computer, 7:21. 10 minutes. See y'all in a moment.